And so I'm going to kind of continue the theme of engineering, but now talk about engineering software. And so I co-founded nTopology. We're a software company based in New York City, Lafayette and Grand Street. We're building next generation CAD design software. And so my talk tonight is really on the data structures that we've been working with over the last three and a half years. But first I'm going to talk about why now, right? Like, why are we looking at new data structures for the design industry? And then I'm going to talk about 3 data structures that we've been using, all based around this idea of a kind of volumetric representation. And I'll get into the 3 as we get going. But first, like, why are we looking at new data structures? CAD is a mature industry. It's been around for 30 years. The most advanced CAD is pretty much unchanged in some ways from when PTC released their parametric modeling. But the thesis we have is that the evolution in manufacturing technology over the last 5 years is basically enabling much more complex parts that can be designed than with traditional CAD. And so there's a term going around the industry right now, generative design, and I think it helps to kind of understand how we define that. And so for us, generative just means capable of production, relating to or capable of production, right? And so I actually don't think generative is that interesting in any way. I actually think engineering itself is generative. But the interesting thing that we're doing is we're actually moving more of that generative process into the computer. And so now the computer is becoming an active component of that design process. And so I think it also helps to look and see kind of what's going on at our customers today. And so within kind of big engineering organizations, you really have a divide between the people who do the design, people who do the analysis, and people who do the manufacturing. And in fact, actually all 3 of these are really important. Both the guy who's actually working on the design, really it can't be separate from the simulation, CAE, or from the manufacturing, the guy in the shop, CAM. And so we see design and optimization kind of encompassing all 3 of these realms, whereas today in most of the industry it's fairly separate and divided. And so then kind of on the workflow side, we're also looking at kind of packaging up components that can be shareable across organizations. So you could think of a common example, ribs and stiffeners. These are used all over the place, right? They're used in pressure vessels, they're used in rib structures. And so we want to basically create a component for that then can be shared and applied within this workflow. And all 3 things are important when you're designing these ribs and stiffeners. The engineering from the analysis side for the physics, manufacturing side, whether it's CNC machine, 3D printed, et cetera, and the design side. And so then again on the workflow, when you look at traditional CAD, it's a very linear process. It's one step after another. You do a sketch in 2D, extrude, offset, extrude, and you tie these steps together. And so again, to create that shareable workflow, we're actually breaking down the design process into a graph. And so that each node in the graph can represent a single operation to create these shareable components. And so then it helps to understand what are the data structures today that are being used. And so CAD is traditionally based on this boundary representation, a BREP. It's an infinitely thin surface representing a part. And so if you look at actual materials in the real world, materials have their properties because of the cellular structure within them. Wood has, long, thin cells, so it's stiff in one axis and not so stiff in the other. And so traditionally, CAD never represented parts like that. They represented parts based on a boundary representation of surfaces, smooth surfaces, but patches. And so it's really kind of a fake. And so then on the analysis side, we actually needed to use a volumetric representation, because when you're running physics on a part, you actually need to understand all the material properties. And so in physics, CAE kind of split early on in the industry into a volumetric representation. But that volumetric representation is discretized. It's stored over discrete tetrahedra filling a volume. And so the advantage in CAD today is that you have these continuous smooth surfaces, but it's a fake. And so it's really hard to model with. You get gaps, overlaps. It's a non-accurate representation of your part. And so if you're trying to, for example, 3D print that part, it's not a representation of the real thing. It's very hard to do. You have to do model cleanup, make sure it represents a volume, et cetera. And then CAE, we have an advantage in that it's a volumetric representation, so it's real, but because it's discretized into these tetrahedra, it's very hard to work with. And so the big question is, how can you still model in a continuous space, but also understand real material properties? And so that kind of takes me to a volumetric representation. And so the idea behind a volumetric representation is that we want to understand the volume of a part. And so we store a function that gives us the distance to the surface. And so anywhere in space, I could know kind of where I am. It's a field to represent the 3D part. And I can vary the material properties, the cellular structure, et cetera, based on that distance to the surface. And so there's a couple ways we've been looking at this volumetric representation. Initially, we started by storing that volumetric function or calculating that volumetric function based on discrete beams and shells. And so in this case, when we started with nTopology, we were looking at building cellular structures or lattice structures. And the idea was we wanted to represent the kind of full design process from concept to manufactured part, but only on a subset of parts initially, just lattice structures. And so in this case, for the lattice, we're basically storing nodes and beams, a graph essentially, with a bucket of nodes and connections between those nodes. And then we're only calculating that surface implicitly. And so there's a major file size savings here when you're storing just the kind of skeleton of the structure versus the traditional mesh representing the surface. About 5%, sometimes even more. And so the idea is we can rebuild the thickness or the meat based on storing attributes at the original nodes. And so we can, at any time, we can go back and forth between this skeleton structure and the volume. And so there's other things we can do using beams and shells. We can store other properties. In this case, for footwear, we can store pressure values over the course of a shoe sole. We can also run an optimization process where now, in this case, we have a block that's a bracket that's fixed on one end, pulled on the other, and we want to get rid of all the material that's not necessary. And so we can go through and change the size of our beams and basically run a physics simulation, and remove the beams that are unnecessary to get our kind of final shape, our final part. Sorry, I just need to escape out of here to go to the next slide. And so we could do the same thing. Instead of connecting with beams, we can also connect with shells. And we can do things like rib structures, origami folded structures, etc. And so with shells, again, now you can do things like the initial workflow for ribs. We did a pressure vessel for a hot part of a rocket that, again, we covered it with these rib structure. And because we were using ribs instead of a solid, thick part, the weight was reduced about 64%. And this is a connector built in the same method. And so in addition to varying properties like size and thickness, we can also vary things like orientation. And so in this case, it's a part that's being twisted under a moment, and the rib structure is now following the optimal stress paths through the part. And again, also locally, the properties are changing, the thickness, the height, etc. But so there's some issues when you're working with just beams and shells as a representation. You actually need that volume to understand really local properties of the part. And so, for example, this is a student we sponsored at NYU's Applied Math Department, and his research was on optimizing on a unit cell level the stresses for a single microstructure cell. And you can see there's really high stresses at the node, varying the thickness of that node. You can remove those stresses. And so instead of just a beam and shell, you need another representation, so another way of storing that volume. In this case, it's called a narrowband level set, and so we're storing that same volumetric function over a small band around the surface. And it's stored under a set of sparse voxels in space to save file size. And so we can calculate these functions off of lots of different things: distance to a surface, distance to a point, distance to a curve. We can also calculate that function based on properties, things like overhang. So when you're 3D printing, for example, most processes, overhang is an important thing. When you're 3D printing in metal specifically, usually you could, depending on the geometry, the overhang angle can not be buildable, essentially. And so we could extract those volumetric functions. In this case, we're building an end effector, and I want to use that volumetric distance to the connectors to spatially vary my internal structure. And so again, I'm gonna extract just the surfaces at the ends that we need. And so this is from our software, from Element, and so I'm gonna extract the distance from the ends, and then project that distance onto the original beam-based structure. So when we're working with these different data models, it's really important to be able to go from one to the other pretty seamlessly. And so then we can use that distance function to drive the thickness attribute of our structure and make a graded structure. And so these are called functionally graded structures. So you can make a structure lightweight where it needs to be and solid where it needs to be, and change the material properties of the part by just changing the unit cells on a kind of local level. And so using this is a discrete volumetric representation. So we can make parts that are around 12 inches squared. But again, because that volumetric function is stored over a discrete set of voxels, it's hard to scale that up. So for small parts, that doesn't matter. But I think the most interesting stuff that we've been working on over the last year is a continuous volumetric representation. So kind of if we go back to the difference between CAD and CAE, it's that people like modeling in CAD because you're working on continuous smooth surfaces versus CAE where you have a discretized volume. And so I think by far the most interesting data structure right now is the functional representation. And this is a continuous smooth volumetric representation. And so the idea with the functional representation is that you're just storing the pure math to represent an exact distance to your surface. So a sphere is represented as square root of x squared plus y squared plus z squared minus r equals 0. Gyroids, which are used, have a lot of applications now for heat sinks. And so gyroids are just sine x, cosine y, et cetera. And so we're storing the pure math function to give us a continuous smooth value to the surface, and then we can extract the surface and render that, which I'm going to get into in a second. And so again, we have this continuous smooth distance field in all of 3D space, and then we're just extracting that surface. And so the nice thing about working with these volumetric representations is that all of your standard CAD operations kind of come for free. So in traditional CAD, Booleans are like one of the most difficult things to do. In functional rep space, a union is just the min, intersection is max, difference is the max of one and the complement of the other. And you can also do things like adding chamfers, adding rounds, like traditional CAD. And again, these are all working on the volumetric function. And so then what you end up getting is you get this big tree of operations, a CSG tree. And so the kind of non-trivial aspect here is, okay, if you're just storing one gyroid, you can query that function really quickly. But as soon as you have up to 40 operations, which is like nothing in CAD, you get this pretty big tree that you have to query. And so the secret sauce or the trick here now really comes down to tree pruning and understanding how to basically not have to query this whole tree every time you want to calculate the distance from a point. And so that tree can get really big. So, okay, so we have this math function that gives us the distance to the surface. So now the question is, okay, how do we visualize it? How do we run physics on it? How do we manufacture it? And so we could, because we have this smooth volumetric function, we can go through and discretize the surface. However, our mesh gets giant here. Even though we have a nice, perfectly smooth part, the mesh that we extract with that at a high tolerance is 7 million faces. And so there's another method we can use for visualization, which is called sphere tracing. This comes from the 70s, a guy named John C. Hart. And the idea here is instead of discretizing to a mesh, to the vertices of a mesh, you're actually discretizing from the pixels on the screen. And so in this case, we can render structures that would be like impossible to mesh. I mean, this wouldn't be impossible to mesh. It would probably be about a gigabyte or so. And then we can also grade our structure. But something like this would probably be impossible to mesh, or a structure like this where you have a unit cell size of it's a 300 millimeter box with a 0.5 millimeter unit cell size. And so I think stuff like this can really start to enable detailed control of the design of really localized properties of a part, like controlling the cells of wood to make custom wood for you. Or we're doing a lot of work with the Air Force in terms of doing really customized material properties of lightweight metal parts. And so then the question is, how do we go to manufacturing, right? So if we can render this, if we can mesh it, we need a way to go to manufacturing. And so the primary kind of manufacturing method that we've been building our software around is metal 3D printing. We're expanding out into other technologies, but if you look at metal 3D printing is driven by layers and slices. And so then the question is, okay, if we have this, smooth volumetric function that gives us the distance to the surface, why can't we do the same thing in 2D and discretize to curves or lines in each slice? And so we've been testing this out, and it's in some builds where we would send a mesh that would take 3 days for a build size that was 50 millimeters in height. Just by sending the CLI file, it's reduced the build time down to about 7 hours. And so it's funny because when people think about 3D printing, they're like, oh, we're going to press a button and get a part immediately. But 7 hours for a metal Inconel part that's 50 millimeters height by 30 centimeters by 30 centimeters is actually really good right now. And so what does that look like now? So then, again, we have our nice continuous smooth part. We slice it up, etc. And a sphere is a sphere. Again, using slices, we can also go to FDM machines. Same method because it's layer-based. And so then the question is, what about physics? Right? And so if we can visualize it, we can mesh it. I have like one more slide left also. So again, we can get our TET mesh from the initial part. But there's a more interesting simulation method that we're researching right now called XFEM. And so this is really where we're embedding that volumetric function into the mesh. And so the researcher who's most well known for this is a guy in CU Boulder, Kurt Mate, who we've been working with pretty closely. And so this is, to me, I think, really the most exciting direction in bringing the physics now back into the process. And so I think, in conclusion, what we've found is really there's not one geometric representation that can solve all problems. There's representations that are optimal for geometry and topology. There might be some that are for simulation. If you can run simulation on it, then you can do your optimization. And then there's probably a separate, more local representation for manufacturing. And so thank you guys for having me. Happy to invite you guys to our office and show you guys some of the parts we've been working on. And thank you.
Thank you very much.
Their phone here, by the way. Yeah. Cool.
All right. Very cool. Thank you. Maybe just to take a quick step back for people that spend less time in this general world. I guess talk to us about the general CAD industry. Who dominates it? What are the current tools that are used, and the major companies?
Yeah, so in kind of high-end CAD, well, there's really 3 incumbent companies that have really kind of become like holding companies for lots of other small companies. So there's Autodesk, there's Siemens, PLM, there's Dassault, and there's PTC. And so the main CAD programs that the people we're working with are using are CATIA from Dassault Systems, and then ProEngineer from PTC, and NX from Siemens PLM. And so all 3 of these software are based on feature-based modeling, parametric feature-based modeling, which is, again, this idea of modeling it. You make a sketch. It's very human-driven, where you have to draw a sketch, and then you apply operations like extrude, offset, loft, etc. You're not defining the problem and then letting the computer algorithm help to design the part. All three of these really were driven by PTC's release in, I think it was 1987, 30 years ago from last year. Pro Engineer, when that came out, it was the first feature-based parametric modeler. And the idea with parametric modeling is you associate dimensions with a sketch and build your part off of that, and then when you change a dimension, kind of history updates. A lot of times if you actually use it, it's actually pretty hard. If you update it, you break your history.
I think you touched upon this at the beginning, but so why, I guess, why now? What is changing fundamentally? Is that more compute power? Is that more university research?
So I think it's actually on the manufacturing side. So things like additive manufacturing, automated wire laying for composites. And so the new, specifically additive manufacturing and 5-axis machining, things like that, are really enabling a lot more complex parts. And people are really quickly realizing that trying to represent a really complex, just a piece of wood, for example, with cells, and then manufacture that, you can't do that using a surface-based representation. Imagine trying to take a piece of wood and for each cell, breaking it down into 4-sided patches around the surface.
It's the fact that you can manufacture it that creates
exactly.
the upstream need for better CAD software.
And I should add, so topology optimization, which is another common algorithm that's been used for generative design, has been around for 30, 40 years. It's only now that the researchers now are like, oh my God, people are so excited by this because we can actually make it. We can make these parts. And so I would argue it's the manufacturing that's driving this.
Very
and then from the CAD side also, the CAD has always been separate from the analysis. The big players in analysis are ANSYS, Simulia, which is part of Dassault.
Very good. All right, question.
So my question was about the analysis aspect. So how easy is it to take the models that you've created and be able to analyze it for displacement and thermal conduction and whatnot?
Well, so the method we're using is a traditional finite element based method. And so in setting up the problem, we usually like it if the person has an analysis background. I think over time what's going to happen is an analyst is going to go in there and set up the material properties, set up the element type, set up the meshing size parameters, and then somebody else can go in there and run that and rerun that. And so within the workflow, somebody who's an expert could kind of dial in let's say the parameters or the ranges, and then somebody who's let's say non-expert, maybe somebody in the field or on the shop floor could be generating parts using that setup. In the software today, it's as easy as clicking on faces and saying, oh, I'm going to apply this load, I'm going to apply this load here. Right now, our solvers, we're only doing linear static analysis, although the stuff we're doing with Kurt is dynamic, transient, vibration, thermal.
So what, how do like materials developers and materials manufacturers sort of get mixed in with the type of work that you do?
Well, so the material developers and the material manufacturers are all giving us specs around their properties. One of the projects we're doing with the Air Force, there's a materials group there at AFRL that is adding a lot of information. The materials guys are all doing very detailed testing on the properties. So there's a whole side I really didn't touch on in this talk, which is like the 3D metal additive parts. The material properties are kind of like all over the place right now, and it's really hard to really relate the parameters that you're using to the material properties that you get out. Sandia Labs had a project where they automated with a robot pulling all of these little tensile bars, and it was like a shotgun of material properties all over the place. And if you build something in the z-axis, it's going to be different than the x-axis. If you build on the x-axis, it's going to be different than the y-axis, which is more surprising. If you build it in one corner of the build, it might be different than in the other corner. And so then it's like, oh, mechanical engineers will say, okay, we'll just heat treat it afterwards, and that'll fix it. And then the material guys are like, well, what do you mean heat treat? Is it an annealing? Is it hipping? Like, where are you stopping the crystal growth of the material? There's a lot of aspects that material scientists are now kind of enabling in the process. I think there's one more question.
All right, one more.
I don't know that I need this thing. You were talking about how there's no linearity or hierarchy like older CAD systems where something builds one after the other after another feature after another feature. Does that actually mean the way your CAD system works that there is no hierarchy? It's entirely solved by the premise of the problem? And follow-up to that would be, like, could you elaborate a little bit more on the setup of your problems? Is it all boundary values and conditions and garbage in, garbage out? Like, how much variation in a material property would hose your simulation, for example?
So that's a really good question, right? So first off, the process that we're doing is a graph where each node in the graph is dependent on the inputs. It's more like functional programming, where you have these independent functions that are tied together, and they're only dependent on what the inputs are. Now, some of these nodes a user could make selection sets based on distances. There's a lot of aspects to the process which are also user-driven and user-defined. Somebody just recently was telling me, like, making a fighter jet is an art. It's not, you're never gonna just set up one problem with all of the boundaries and get a fighter jet out by pressing a button. And so I think there's this, like, goal of a lot of people in the industry to basically make it so that, you know, or to pitch that, oh, we're gonna build a CAD system where you press a button and you get a part. And, like, the engineers that we've been speaking to are really, they're like, it's just not gonna work. And you'll never be able to define all of the boundary conditions in the correct way. And so I think what I'd like to push more is really, let's say it's like more of a messy process where you have engineering input for each of those steps. Now, specifically when you're setting up a specific algorithm like topology optimization, you know, if you're calculating the sensitivities off of, you know, varying the thickness of the beams and then they become solid, or if you're doing a density-based topology optimization or the XFEM-based topology optimization, in that case you are setting up boundary conditions. What we found is actually just applying a little stochastic random strain around the initial conditions that you get more robust parts. So there's things like that, but I think that's the major problem with, like, computational or algorithmic based design, is that if you don't know what the inputs are, the output's not going to be good. And so then a lot of times you have to go back, tune it, and then get another output. I'd like to think that, like, with a smooth, continuous volumetric representation, once the algorithm comes out, if you as an engineer look at that and you're like, oh, actually I want to make this hole a little bit bigger, you don't have to go back to the beginning and reset the problem and run it to try and make the hole bigger. You can just go in there and click on that hole and make it bigger or offset it. Cool. Thank you.
Thank you very much.